In the stillness of night, when the air grows quiet and the earth drifts into shadow, the sky reveals its ancient secret. Countless stars glimmer across a dark ocean, each one a distant sun, each one a silent beacon of time. The human gaze, fragile, yet unyielding, rises to meet them, reaching for patterns in the void. But beyond those constellations, beyond even the farthest galaxies our telescopes can touch, lies a question older than civilization itself. How vast is the universe? Does it stretch without end, an infinite tapestry of stars and silence? Or does it curve back upon itself, like the surface of a sphere, immense yet finite, holding us within boundaries we cannot yet perceive? Humanity has always looked outward, chasing horizons across deserts, oceans, and skies. Each frontier has eventually revealed its edge. But what happens when the frontier is the universe itself, when no horizon holds still, when the edges retreat faster than we can approach? Every measurement, every calculation, every refinement of our cosmic tools leads not to answers but to expansion. The universe grows larger with every revelation. Its horizon slips further with every glance. What seemed finite yesterday appears infinite today. It is a paradox, both scientific and deeply human. The more we know, the more vast the unknown becomes. The size of the universe is not just a question of distance and scale. It is a mirror reflecting the limits of our knowledge and the boundless reach of our imagination. And so, beneath the endless night, one question lingers. How big is our universe? And will we ever truly know? The night sky has always been humanity's first great book. Long before ink touched parchment, before stone carried inscriptions, the stars wrote their stories across the heavens. To the earliest civilizations, these lights were not just ornaments of the night, but signs, maps, and mysteries, fragments of eternity scattered over mortal lives in ancient Mesopotamia. The Babylonians watched the heavens with a persistence that bordered on devotion. They charted the motions of planets with clay tablets, etched with cuneiform marks that still whisper across the ages. For them, the sky was a clock and a calendar, its shifting patterns guiding the planting of crops, the timing of rituals, the rise and fall of kings. But beneath their records lies a deeper wonder, the attempt to grasp the scale of the cosmos. How far did these wandering stars travel? Was there an edge where the dome of the sky touched the earth? Or did the heavens extend endlessly, a kingdom with no walls? To the Mayans, across the oceans and centuries, the cosmos was a living order, woven into cycles of time. Their codices tell of the careful tracking of Venus, of eclipses and solstices. Their temples aligned with celestial events, each stone lifted into place as a bridge between earth and sky. Yet even here, in the jungles of Central America, the same haunting question lingered: what lies beyond? The gods and myths filled the silence with stories, but the human eye searched for scale. In Greece, philosophy sharpened this search into a blade of reason. Aristotle, standing in the 4th century BCE, imagined a cosmos that was finite, perfect, and complete. To him, the heavens were crystal spheres, each carrying a planet or a star, all encased within a grand celestial shell. The universe had an edge, a boundary, where the stars themselves were fixed like jewels upon a perfect dome. Beyond that dome, there was nothing, not emptiness, not voids, simply non-existence. It was a vision of closure, of limits. Yet not all thinkers were content with Aristotle's finite sky. Democritus, centuries earlier, had whispered of infinite worlds, scattered like dust across an endless expanse. To him, the universe was not a single stage, but an infinite theater, with countless suns, countless earths, and perhaps countless lives. His vision was radical, unsettling, and fragile in a world that preferred the comfort of boundaries. Still, the seed was planted. Perhaps infinity was not a concept of gods, but a feature of nature itself. Philosophy, myth, and measurement braided together into humanity's first attempts to size the cosmos. Myth gave narrative, philosophy gave logic, and measurement gave numbers, however small or symbolic they seemed. The Egyptians marked time with the rising of Sirius, their calendars bound to the flooding of the Nile. The Chinese, with meticulous records, tracked comets and novae, some of which modern astronomers still confirm as the first known supernova. Each culture, in its own way, turned eyes skyward, not only for guidance, but for scale. And yet, for all their differences, a universal thread ran through these early visions. The cosmos was larger than the human mind could contain, and still not large enough to escape imagination. The first true instruments of measurement were simple but profound. The gnomon, a stick planted in the earth, cast shadows that told of the sun's journey. The astrolabe, born in the Hellenistic world, became a handheld cosmos, a disk of brass and geometry that mirrored the heavens in miniature. With it, scholars could trace the altitude of stars, predict the rising of constellations, and orient themselves upon the earth. In its turning plates lay the suggestion of something greater, the possibility that the universe could be measured, piece by piece, angle by angle. Star charts followed, ink on parchment, capturing the slow crawl of celestial lights. To hold such a chart was to hold a fragment of the universe in one's hands, a map, not of oceans or continents, but of infinity itself. These were not yet precise measurements of cosmic scale, but they were the first footsteps into a journey that would never end. Even in their myths, humanity revealed a restless drive to size the universe. The Babylonians imagined the heavens as a great canopy, upheld by mountains at the edges of the earth. The Norse spoke of Yggdrasil, the cosmic tree that bound the 9 realms. The Hindus envisioned cycles of creation and destruction, universes born and dying across stretches of time so vast they defy modern numbers. These were not idle stories. They were metaphors for scale, attempts to grapple with the immensity of existence using the tools of narrative when mathematics was still young. But philosophy did something myths could not. It asked whether the universe was finite or infinite, and demanded an answer not of gods, but of reason. The Stoics leaned toward a cosmos that was cyclic, eternally repeating. The Epicureans imagined boundless space, populated with endless atoms, forming endless worlds. Here lay the seeds of debate that would echo for millennia. Is the universe a bounded whole or an infinite expanse? Aristotle's finite cosmos endured for centuries, given authority by the weight of his name. It was a comforting vision, a universe, complete, ordered, and knowable. But the human eye was not content. Observers noticed wandering stars, the planets that did not move like the rest. Astronomers built models, concentric spheres within spheres, to preserve Aristotle's perfection. Yet, with each refinement, the machinery grew more strained, as though the universe resisted confinement. Still, in these struggles lay progress. Each astrolabe calibrated, each chart refined, each debate argued beneath the flickering light of oil lamps, brought humanity closer to what the universe truly was. Not a stage bounded by crystal shells, but something far greater, more mysterious, and more vast than the ancient mind could yet conceive. In these first questions, the paradox was born. To measure the universe was to try to measure infinity. To grasp its size was to touch the limits of imagination itself. The Babylonians did not know of galaxies, but they knew the heavens stretched far beyond their cities. The Mayans did not speak of light years, but they sensed cycles of time that reached into eternity. The Greeks did not calculate cosmic expansion, but they laid the philosophical foundations that would confront it. Thus, the first cosmic questions were asked, not with telescopes, not with satellites, but with wonder, myth, and reason. They were questions carved into stone, painted on temple walls, whispered in philosophy's earliest schools. And though their answers were incomplete, even flawed, they marked the beginning of humanity's greatest pursuit. For beneath all their charts, myths, and philosophies lay a single, enduring question, the same one whispered under stars tonight. How big is our universe? For thousands of years, the stars were fixed points upon a dome, eternal and unchanging. The human eye, though filled with wonder, could see only so far. But then, in the early 17th century, a simple tube of glass and metal transformed perception forever. The telescope, small enough to rest in human hands, became a portal to the infinite. When Galileo Galilei lifted his telescope toward the night sky in 1609, the heavens trembled. Through that narrow cylinder of glass, Jupiter no longer stood alone. 4 moons circled it, tiny worlds locked in their own rhythm. The moon itself, once thought smooth and perfect, revealed mountains and craters' imperfections carved in shadow. And beyond, the Milky Way, once a faint mist, dissolved into countless stars, too numerous for the naked eye to count. The cosmos had expanded, not in size, but in perception. What was once a ceiling now appeared as an ocean, layered with hidden depths. Galileo's discovery shattered the crystalline spheres of Aristotle's cosmos. The universe was no longer a polished dome, but a realm of endless complexity. Centuries passed, and the telescope grew more powerful. Mirrors replaced lenses, observatories crowned mountaintops, and astronomers peered deeper into the night. The sky that once seemed static began to whisper secrets of change. In the early 20th century, a young astronomer named Edwin Hubble, working with the 100-inch Hooker telescope atop Mount Wilson in California, peered into faint smudges of light. For generations, these smudges were thought to be clouds of gas within the Milky Way. But Hubble's observations revealed something astonishing. These were not clouds. They were galaxies' vast islands of stars, far beyond our own. The universe was larger than anyone had imagined, but the revelation did not end there. By analyzing the light of these galaxies, Hubble discovered a strange truth. Their light was stretched, shifted toward the red end of the spectrum. The greater the distance, the greater the shift. It was as if the galaxies themselves were fleeing, carried away on invisible currents. In 1929, Hubble published his results. He had uncovered a law that would forever change humanity's place in the cosmos. The farther a galaxy was, the faster it receded. Distance and velocity were linked by a simple equation: cosmic scale. The implications were staggering. The universe was not fixed. It was expanding. The fabric of space itself was stretching, carrying galaxies apart like leaves drifting on an ever-widening river. This was not just a scientific discovery, it was a philosophical earthquake. For centuries, the universe was thought to be eternal, unchanging, a stage upon which stars lived and died. But Hubble revealed a universe alive with motion, dynamic and unfinished. If smaller, then perhaps there was a beginning. The human mind reeled at this thought. The universe was not an endless, static backdrop, but a story with chapters, a cosmos with a past, and perhaps a future. To visualize Hubble's discovery is to imagine the surface of a balloon dotted with stars. As the balloon inflates, each dot drifts farther from the others. No single star is the center, yet all move apart. So too does the universe expand, not into space, but of space itself. Every galaxy, every cluster, carried outward by the stretching of the cosmic fabric. For the first time, humanity could assign numbers to the unimaginable. Hubble's constant measured the rate of expansion, a cosmic heartbeat echoing across billions of light years. With it, astronomers could begin to calculate distances on scales once reserved for myth. The size of the observable universe unfolded in staggering details of billions of light years, filled with billions of galaxies, each a city of stars. Yet with discovery came unease. If the universe was expanding, what was it expanding into? If galaxies receded endlessly, did that mean the universe itself was infinite? Or had it all begun from a single point, an origin too dense and too hot for comprehension? The questions deepened as quickly as the answers emerged. The emotional weight of Hubble's discovery cannot be overstated. Humanity had always sought stability in the heavens' patterns, cycles, eternal return. The expansion revealed a cosmos without fixed boundaries, without permanence, where even the stars themselves were participants in a vast unfolding. It was not merely science. Scale. In the decades that followed, the expansion of the universe became the foundation of modern cosmology. The Big Bang Theory arose, built upon the framework Hubble had revealed. Observations from ever more powerful telescopes confirmed the drift of galaxies, mapping a universe alive with motion. What Galileo had glimpsed through a modest lens was now an entire cosmos in flux, a story still being written. Yet even as equations refined and measurements sharpened, the mystery only deepened. The expansion was not uniform, not simple. Some regions moved faster, some slower, and beyond the observable horizon, nothing could be seen at all. The sky no longer offered a finite stage, but an ever-receding frontier through Galileo's lens. The universe first revealed its hidden multiplicity. Through Hubble's telescope, it revealed its restless expansion. Each step stretched imagination further, forcing humanity to reconsider what size even meant, growing larger with every passing moment. And so the story of measurement shifted from myth to mathematics, from speculation to observation. The telescope had become the bridge. With it, the human mind touched infinity not in completion, but in pursuit. The expanding sky was no longer just a question of what lay beyond. It became a question of time itself. For if the universe expands, then it evolves. If it evolves, then it began. And if it began, then the horizon ahead is as uncertain as the one behind. Thus, with glass and mirror, with patience and wonder, humanity unlocked a truth both exhilarating and unsettling. The universe is not still. It is a journey carrying galaxies, stars, and even the observers themselves outward into an ever-widening unknown. The telescope had shown that to ask how big the universe is also to ask how long it has lived and how far it will go. A question not of boundaries, but of becoming. The universe speaks to us in light. Every star, every galaxy, every fragment of matter that has ever burned or scattered photons leaves a trace upon the cosmic darkness. Light is not only illumination, it is a messenger traveling across the abyss with the stories of distant worlds, but in its speed lies both a gift and a limit. For light, swift though it is, does not travel instantly. It takes time, and in that time it carries with it the boundaries of what can be known. At 299,792 kilometers per second, the speed of light is the ultimate ruler of reality. This speed defines the horizon, a vision, a barrier that is not chosen by instruments, but by the very laws of nature. Humanity can only see as far as light has traveled since the beginning of time. Beyond that, the universe remains veiled, invisible to any eye, any telescope, any dream. Thus emerges the idea of the observable universe. From Earth, or from any vantage point in space, a sphere surrounds the observer, a bubble of visibility, defined not by walls, but by time itself. Light that has had 13.8 billion years to travel reaches us from galaxies unimaginably distant. Their glow, stretched and reddened by the expansion of space, whispers across eternity into our instruments. What we see is not their present, but their past, the shadows of what they once were, projected upon the fabric of the sky. Yet here lies the paradox. If the universe is 13.8 billion years old, should the observable horizon not lie 13.8 billion light-years away? And yet, measurements tell a different story. The cosmic bubble stretches far wider. The observable universe is not 13.8 billion light-years in radius, but almost 46 billion, from one edge to the other. It spans about 93 billion light-years across. The explanation is as profound as it is unsettling. Space itself expands. While light journeys across the void itself stretches beneath it. Galaxies that emitted their light billions of years ago are now far beyond the simple measure of time multiplied by speed. The universe has been growing during the voyage of every photon, pulling distant galaxies farther and farther away. We do not see them where they are, but where they once were, their present distance far beyond what their light suggests. In this way, the observable universe becomes a paradoxical mirror. It shows us the past, not the present. It reveals the ancient, not the immediate. The galaxies we see at the horizon may already lie far beyond reach, some perhaps extinguished, their light the final echo of their existence. To observe the cosmos is to watch a memory of film projected across spacetime, with each frame delayed by billions of years. The scale defies imagination. Within this 93 billion light-year bubble lies an estimated 2 trillion galaxies, each containing hundreds of billions of stars. Between them, vast cosmic voids stretch across millions of light-years. Nearly empty expanses separating filaments of clustered galaxies that weave a web-like structure, the cosmic web. The observable universe is not uniform, but textured, sculpted by gravity into patterns larger than anything the human eye can truly conceive. Yet, beyond the horizon, silence reigns. The universe does not end there, but its light has not yet arrived. There may be galaxies, structures, perhaps even forces unknown, all hidden beyond the reach of vision. Our instruments cannot pierce this horizon, not because of failure, but because the laws of physics forbid it. The cosmic horizon is not a wall, but a limiton event boundary, set by the age of light itself. To imagine it is to imagine standing in the center of a vast bubble, expanding outward in all directions. The edge of the bubble is not solid, is simply the farthest distance light has traveled since the dawn of time. Every observer, no matter where they are in the universe, would find themselves at the center of their own bubble. There is no single vantage point privileged above others. Each location holds its own horizon, and beyond each, an unseen expanse continues. Philosophically, this creates a tension both haunting and profound. The universe does not end at what we can see. It continues, perhaps infinitely, beyond the observable bubble. What lies beyond remains forever unmeasured, concealed, not by distance, but by time. And yet, even this limitation is part of the beauty. The horizon is not a failure, but a definition, a reminder that to measure the universe is to measure history itself. When astronomers calculate the scale of the observable universe, they are not merely drawing lines across space. They are tracing the age of existence. Each photon from the cosmic microwave background, discovered by Arno Penzias and Robert Wilson in 1965, carries with it the echo of the Big Bang, light, stretched over 13.8 billion years. This radiation, faint but all-encompassing, forms a wall of light that marks the earliest moment we can observe. Beyond it, the universe was opaque, too dense, too hot for light to travel freely. The observable universe is thus also a temporal horizon, the farthest we can peer into the past, and so the bubble stands as both a measurement and a metaphor. It is the sum of all that can be known, the totality of cosmic history visible to us. It grows with time, as light from ever more distant galaxies finally arrives. Yet it also shrinks in possibility, as the expansion of space accelerates and distant regions slip forever beyond reach. The horizon is both promise and prison. To ask how big the observable universe is to ask how long the cosmos has endured. Its size is inseparable from its age, its boundaries inseparable from its expansion. The 93 billion light-year expanse is not the measure of the universe itself, but of our ability to see it. What lies beyond remains an open question, suspended between science and speculation. Perhaps the universe continues without end, infinite in every direction, repeating patterns forever. Or perhaps it curves back upon itself, a finite yet unbounded structure, like the surface of a sphere, where traveling far enough in one direction would eventually bring one back to the beginning. Both possibilities remain mathematically and philosophically alive, suspended within the equations of general relativity and the measurements of cosmic background radiation. But within the observable horizon, one truth resounds. The universe is not a still portrait. It is an unfolding film, projected at the speed of light, revealing not where things are, but where they were. To gaze into the night is to gaze into memory, into history, into the very origins of time. Thus, the observable universe is not a cage, but a reminder. Its edges are not walls, but horizons, forever retreating, forever inviting. Humanity may never see beyond its bubble, but within it lies a grandeur that dwarfs imagination, a 93 billion light-year stage upon which the story of existence unfolds. And in that vastness, the paradox endures. The more we measure, the larger the horizon grows. The more we discover, the more distant the unseen becomes. The observable universe is not the end, but the beginning of mystery. Ages for the arc of a day. Yet, when astronomy widened its gaze, numbers began to rise into territories that language itself strains to hold. Within the observable universe alone, astronomers now estimate there are perhaps 2 trillion galaxies. Each galaxy is a city of stars, many with hundreds of billions, some with trillions. The Milky Way itself, with its 100 to 400 billion stars, is but one spiral among uncountable swarms. If every star were a grain of sand, the beaches of Earth would seem small compared to the cosmic shore. This immensity shocks not only the imagination, but also science itself. For science thrives on measurement, and measurement thrives on limits. To measure is to define. But how does one define a universe that appears not only vast beyond comprehension, but possibly endless? Here lies the contradiction. Observations show a finite bubble, the observable universe, bounded by the distance light has traveled since the Big Bang. Within this horizon lies structure, form, data, galaxies mapped, redshifts measured, cosmic background radiation traced. Yet theory and mathematics suggest that beyond this bubble, space continues, perhaps a little farther, perhaps without end. The observable universe may be only a small fraction of a reality that extends forever. Infinity enters the story here, and with it unease. Infinity is not a number. It does not sit neatly in equations. In physics, infinity is a signal that something has broken, that an equation has reached beyond what it can describe. When infinity appears in calculation, it is a red warning light, a reminder that human models are incomplete. For this reason, many physicists hesitate to speak of the universe as infinite. They choose instead the word unbounded. A sphere, for instance, is finite in surface area, yet has no edges. One can travel endlessly without encountering a wall. In the same way, space may be finite, yet unbounded, wrapping back upon itself in dimensions that defy visualization. To call it infinite is to abandon measure. To call it unbounded is to preserve possibility, and yet, even the concept of unbounded carries with it a weight that bends the mind. For if the universe wraps upon itself, then every journey is a loop, every path a return. But if it is truly infinite, then the implications grow stranger still. An infinite universe would mean infinite stars, infinite galaxies, infinite arrangements. of matter. Somewhere in the unfathomable distance, configurations identical to ours would recur. Infinite versions of Earth, infinite versions of each observer. Such speculation, though mathematical in origin, touches the borders of philosophy, where identity and uniqueness dissolve into endless repetition. This is the scientific shock. Not only is the universe larger than the human mind can contain, it also resists the very methods by which the mind seeks to measure it. Numbers climb into scales where meaning thins. Trillions of galaxies, quintillions of stars, distances in billions of light years. Each is real, yet each pushes language toward abstraction. Even Einstein struggled here. His equations of general relativity allowed for universes that were infinite, but he himself leaned toward models that were bounded. An infinite cosmos seemed too unruly, too unmeasurable. Later, physicists wrestled with the same discomfort. Hawking described infinity in physics as a sign that we are missing something fundamental. For infinity is not just large, it is limitlessness, and limitlessness defies science. Still, the data persist. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, suggest a universe that is remarkably flat. If space were curved tightly enough to be finite, the background would reveal it. Yet all observations to date show a cosmos flat to extraordinary precision. Flatness implies continuation. Continuation implies boundlessness. The evidence points not to walls, but to horizons that retreat forever. And so science lives with paradox. A finite observable universe 93 billion light-years, a cross-nested within a possibly infinite reality. An island of measurement floating on an ocean without shores. For the human spirit, this paradox is both humbling and unsettling. To know that all of history, all of civilization, all of life occurs within a single galactic neighborhood of an unfathomable expanse is to confront smallness on a cosmic scale. Yet it also evokes wonder. The universe resists containment because it was never meant to be contained by thought alone. It is larger than comprehension, and perhaps that is its most profound truth. Thus, the scientific shock is not only numerical, it is existential. To face a universe that may be infinite is to face the limits of science itself and the limits of the human mind. The question is no longer merely how big is the universe, but can size even be defined when boundaries may not exist? Infinity unsettles because it denies final answers. Yet it also compels, for it is in chasing the immeasurable that humanity discovers the depths of its own curiosity. The universe carries a memory, not written in stone or in fossil, but in radiation that fills all of space. It is faint, almost imperceptible, a whisper in the fabric of existence. And yet, within this whisper lies the most profound clue to the size and shape of the cosmos. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, stumbled upon a signal they could not explain. Their antenna, designed for satellite communications, picked up a persistent hiss of microwave radiation. They checked their instruments, recalibrated their equipment, and even cleaned away nesting pigeons from the antenna's horn, suspecting the birds were to blame. But the signal remained. It was uniform, constant, coming from every direction. In the sky what they had found was nothing less than the afterglow of creation itself, the cosmic microwave background, or CMB. This radiation, emitted nearly 380,000 years after the Big Bang, was the first light of the universe, released when matter cooled enough for atoms to form and photons to travel freely. Before this moment, the universe was opaque, a hot plasma where light could not escape. With the birth of atoms came the birth of transparency, and the universe's first visible memory was set free. The CMB is more than relic. It is a map, a frozen imprint of the infant cosmos. Its faint variations in temperature, only millionths of a degree, reveal the seeds of structure, the ripples of density that would one day form galaxies, stars, and planets. It is, in essence, the universe's birth photograph, stretched across the entire sky. But beyond its beauty lies its power. By studying the patterns of the CMB, scientists found a ruler with which to measure the cosmos. The size of the hot and cold patches, their distribution across the heavens, depended on the geometry of space itself. If the universe were closed, like the surface of a sphere, light would curve, and the patterns would appear larger. If it were open, like a saddle, they would appear smaller. If it were flat, the patterns would remain at their true scale. In 1989, NASA launched the Cosmic Background Explorer, or COBE, to study this radiation with precision. COBE confirmed what Penzias and Wilson had discovered, but with a clarity that stunned the world. The universe was filled with this ancient glow, almost perfectly uniform, but with delicate ripples that matched the predictions of the Big Bang. George Smoot, one of COBE's lead scientists, described it as seeing the face of God. The work did not end there. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP. Over 9 years, WMAP mapped the CMB with extraordinary detail, tracing its fluctuations across the entire sky. From these maps, scientists derive the age of the universe 13.8 billion years with remarkable accuracy. They measured the proportions of its contents, dark energy, dark matter, and ordinary matter, and they turned their eyes to its shape. What they found was astonishing. The data revealed a cosmos that is flat, not curved, to within a fraction of a percent. Space, across the vast observable universe, did not bend inward like a sphere, nor outward like a saddle. It stretched, instead, in perfect balance. Flatness has profound implications. A flat universe suggests that it could extend without end, just as a flat sheet of paper, if stretched forever, has no boundary. So too might the universe continue infinitely in all directions. Within the observable bubble, finite and measurable, lies the suggestion of an unbounded cosmos, stretching beyond the horizon into realms unseen. In 2009, the European Space Agency launched Planck, the most sensitive CMB mission to date. With unprecedented precision, Planck refined the cosmic map, resolving fluctuations with exquisite clarity. Its data confirmed WMAP's results. The universe is flat to extraordinary precision. If there is curvature, it is so slight that it would take a universe hundreds of times larger than the observable one to reveal it. The shock lies not only in the precision, but in the consequence. A flat universe, extending beyond our horizon, points toward a reality that may be infinite, though infinity cannot be proven. the evidence resists boundaries. If the cosmos is not infinite, then it is so vast that infinity becomes indistinguishable from reality. Here, science collides with philosophy. Infinity is not just a number. It is a concept that unravels meaning. If the universe is infinite, then every possible configuration of matter exists somewhere. Every galaxy that could be is. Every planet that could form does. The uniqueness of Earth dissolves into repetition across boundless space. The human mind reels at such possibility, caught between awe and disquiet, and yet flatness does not answer every question. The CMB is a map of the early universe, not of its totality. It tells us how the cosmos began, not how far it extends. There remains the possibility that the universe, though flat on observable scales, may curve on scales far larger, bending in ways forever beyond detection. It may be finite, like a vast but unbounded sphere, its closure too distant to measure. Or it may indeed be infinite, a flat expanse without end. The CMB has thus deepened the paradox. It has given science extraordinary power to measure, yet it has left the ultimate question unresolved. The observable universe is finite, but the reality beyond may be boundless. The first light of creation shows us the shape of space, but not its limits. To gaze upon the CMB is to gaze upon time itself. The radiation carries with it the story of a cosmos only a fraction of 1,000,000 years old. It is a reminder that the vastness of today was once a fireball of unimaginable density, that the infinite silence of space once rang with the roar of birth. The discovery of the CMB, from the static of an antenna in New Jersey to the precision of satellites orbiting Earth, marks one of humanity's greatest achievements. It has shown that the universe is comprehensible, yet incomprehensibly vast, that its shape can be measured, even if its size eludes final definition. And so, in the quiet hiss of microwave radiation, the universe has spoken. It has revealed its age, its composition, its geometry, but it has withheld its final secret, its size. For in the flatness of space lies the possibility of infinity, and with it, the humbling truth that the cosmos may be larger than science can ever declare. The CMB is both answer and invitation, a signal from the past that illuminates the present, and a reminder that the greatest questions still lie beyond the horizon. The universe was already immense, already expanding, already difficult for the human mind to hold. But at the turn of the millennium, a discovery arrived that transformed vastness into something even more unsettling. The revelation that expansion itself is accelerating. It began with an effort to measure the universe's fate. Astronomers had long debated whether gravity, the great sculptor of structure, might one day slow expansion and pull everything back into collapse, or whether the universe would continue to drift outward forever. To answer this, two teams set their gaze on distant type Ia supernova, stellar explosions so bright they briefly outshine entire galaxies. Their uniform brightness made them cosmic lighthouses, standard candles by which distance could be judged across billions of light-years. In 1998, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, delivered a result that shocked the world. Instead of slowing down, distant galaxies were receding faster than expected. The universe was not merely expanding, it was accelerating. The implications were staggering. To accelerate requires energy, yet no known force could explain it. Gravity pulls, it does not push. Matter attracts, it does not repel. Somewhere in the equations of cosmic motion, a new term had to exist, a force unseen yet all-pervasive. It came to be called dark energy. Dark energy is not matter, not light, not any particle ever measured. It is an intrinsic property of space itself, a pressure woven into the vacuum, stretching space-time outward. Its strength is faint, almost imperceptible on human scales, yet across cosmic distances it dominates. Today, dark energy is thought to make up nearly 70% of the universe, silently dictating its future. With this discovery, the universe became stranger than ever imagined. Expansion was not slowing toward equilibrium. It was racing into the unknown. Galaxies once within sight would slip beyond the cosmic horizon, their light stretched until it could no longer reach us. The observable universe, though still vast, would grow increasingly empty. A horizon that retreats faster than light ensures that some parts of the cosmos will remain forever hidden, not by distance alone, but by the nature of space-time itself. This is the paradox of acceleration. The more we search for the universe's totality, the less of it we will ever see. Expansion ensures that all is unreachable, that beyond the horizon lies not merely the unseen, but the forever unseeable. Science confronts here not only immensity, but inaccessibility. The philosophical weight of this revelation is profound. A static universe suggested permanence. An expanding universe suggested history and change. But an accelerating universe suggests an eternal retreat, where every answer opens onto more questions, and where the boundaries of knowledge are written, not in instruments, but in the laws of nature. Dark energy, though dominant, remains deeply mysterious. Is it a constant, woven into the fabric of space-time, as Einstein once imagined in his cosmological constant? Or is it dynamic, a field that changes with time, whose strength may one day alter or fade? Observations from the Hubble Space Telescope, the Sloan Digital Sky Survey, and more recently from missions like DESA and Euclid, attempt to trace its behavior, measuring the subtle changes in galaxy clustering and cosmic structure. Yet answers remain elusive. What is known is unsettling enough. If dark energy remains constant, the universe will expand forever, accelerating endlessly. Galaxies vanishing beyond the horizon until only local clusters remain. Stars will burn out, matter will decay, and the cosmos will drift into heat death. Silence of infinite expansion. If dark energy grows stronger, a big rip awaits, where even atoms are torn apart by space-time's relentless stretch. If it weakens, gravity may yet reassert itself, though evidence for such reprieve grows thinner with every observation. The scale of cosmic size is thus no longer only spatial, but temporal. The horizon retreats, not only in distance, but in time, promising that future observers will see less of the universe than present ones. The night sky, now rich with galaxies, will one day fade into emptiness, the lights extinguished not by their death, but by their disappearance beyond reach. Humanity stands in a privileged era when the cosmic expanse is still visible, when the evidence of acceleration is still within sight. In this way, The discovery of acceleration reshaped the meaning of cosmic size. The universe is not only vast, is growing more vast at an ever-quickening pace. Its true extent cannot be mapped because its borders are not fixed. The horizon flees faster than pursuit, carrying secrets forever away. Here, science encounters not just immensity, but futility. No telescope, no matter how powerful, can pierce beyond a horizon that recedes faster than light. No equation, no matter how elegant, can transform the unreachable into the reached. Dark energy has written into the cosmos a permanent limit, a wall not of matter, but of time and expansion. And yet, in this futility lies wonder. For to live in an accelerating universe is to live within a story still unfolding, a cosmos not static but dynamic, not eternal but evolving. The mystery of dark energy is not a barrier but an invitation, a reminder that the universe is larger, stranger, and more alive than comprehension alone can hold. Thus, the escalation is complete. From Galileo's telescope to Hubble's law, from the cosmic microwave background to the discovery of acceleration, each step has stretched the meaning of size beyond imagination. The universe is not just big, it is in motion, and that motion grows ever faster. Its horizon is not an edge, but a retreat, a boundary that deepens with every moment. The shock of acceleration is not only scientific, but existential. To live in such a universe is to live within a mystery that cannot be solved, only approached. The cosmos stretches away, and with it, human understanding. Yet even in retreat, it reveals the boundless capacity of curiosity to ask, to measure, to imagine against a backdrop that will always be larger than the question. The universe expands. The universe accelerates. And with every passing moment, all slips further beyond reach. The discoveries of expansion, flatness, and acceleration have not closed the question of the universe's size. Instead, they have widened it into realms where science borders philosophy and mathematics touches the infinite. What lies beyond the observable horizon? Does the universe end, or does it continue without limit? Three possibilities stand before modern cosmology, each unsettling, each profound. Possibility 1, finite but unbounded. One vision suggests the universe is vast but closed, finite yet without edges. To imagine it, consider the surface of a sphere. A traveler walking endlessly across its surface never meets a wall, never falls from its edge. And yet the surface is finite. Its area is measurable, its totality contained. Einstein's general theory of relativity allows for such a structure, extended into 3 spatial dimensions. In this vision, the universe is a 4-dimensional analog of a hypersphere. Its curvature is subtle, so subtle that across observable scales it appears flat. But on scales beyond our horizon, space might wrap back upon itself, connecting distant points in ways beyond human perception. In such a universe, a photon traveling long enough in one direction might eventually return to its point of origin, not because it was reflected, but because space itself curved. Galaxies might repeat across the sky, their images arriving from different paths through curved spacetime. This vision offers comfort to some physicists. A finite universe is measurable, even if incompletely. It avoids the conceptual chaos of infinity, preserving a cosmos that, though immense, is still comprehensible in principle, yet it carries its own unease. A finite cosmos is a closed hole with no outside. Beyond its surface lies not space, but nothing, not emptiness, not void, but non-existence. For the human imagination, trained to place objects within larger contexts, this absence is as troubling as infinity itself. Possibility, too, truly infinite, the second vision, is more radical. The universe is infinite, stretching endlessly in all directions. Here, space is not curved into closure, but flat without end. If the universe is infinite, then within it lies not only countless galaxies, but unbounded repetition. Every possible configuration of matter, given infinite trials, will occur. Somewhere, an identical Earth spins around an identical sun, with identical histories unfolding. Somewhere further still, variations arise, worlds almost the same, yet subtly different. The concept of infinity transforms uniqueness into pattern. What feels singular becomes inevitable. Human existence, under infinity, is not one occurrence, but one of endless echoes. This is not speculation born of fantasy, but of mathematics. If the universe is infinite, and matter is arranged randomly across it, then probability demands repetition. For physics, infinity is both liberating and destabilizing. Liberating because it explains flatness and avoids the need for cosmic closure. Destabilizing because infinity resists measurement. Equations with infinity often diverge, producing paradox instead of prediction. Infinity undermines the very principle of science, which depends on boundaries, definitions, and testable quantities. Some physicists, therefore, hesitate to declare the universe infinite. They prefer to speak of it as effectively infinite, so large that, for all practical purposes, it is without end. Yet the philosophical consequences remain the same. Infinity strips away the human sense of center, leaving only boundless repetition and unending scale. Possibility 3. The multiverse. The third vision goes beyond space and into the possibility of multiple universes. Our cosmos may not be the only one. It may be one bubble in a vast and eternal inflationary sea. The idea arises from inflation theory, first proposed in the early 1980s by Alan Guth, Andre Linde, and others. Inflation suggests that in the earliest fraction of a second after the Big Bang, the universe expanded at a staggering rate, far faster than today's acceleration. This rapid inflation smoothed the cosmos, producing the uniformity seen in the cosmic microwave background. But inflation may not have ended everywhere. In some regions, quantum fluctuations could prolong inflation indefinitely, spawning new bubble universes as others slow into expansion. This process, known as eternal inflation, would create not one universe, but an endless froth of them, each with its own laws, constants, and structures. Our observable cosmos would be a single bubble among countless others, adrift in an inflationary ocean. Stephen Hawking wrestled with this vision, suggesting that quantum fluctuations at the dawn of time could give rise to entire universes. Andre Linde expanded upon the concept, imagining a multiverse eternally generating new realities. In this model, the cosmos has no single size. It is not finite, not infinite, but plural, an endless branching of universes, each with its own horizon. The multiverse is both fascinating and terrifying. Fascinating because it offers explanations for mysteries such as why the laws of physics appear fine-tuned for life in an infinite ensemble of universes. Ours may simply be one where conditions allow observers to exist. Terrifying because it renders our universe less significant, one of uncountable worlds, each as real yet forever inaccessible. Quantum fluctuations and eternal creation. At the heart of both infinity and the multiverse lies quantum theory. The vacuum of space is not empty but restless, filled with fluctuations that pop into existence and vanish in an instant. These fluctuations, when magnified by inflation, can seed entire universes. In this sense, creation is not a singular event, but an ongoing process. The notion is staggering. Universes budding forever, each with its own expansion, its own galaxies, perhaps its own observers. In this framework, asking how big is our universe becomes incomplete. The question shifts to how vast is the ensemble of universes. A question, perhaps, beyond even speculation. Why each theory terrifies and fascinates each possibility, stretches the imagination to its breaking point. A finite but unbounded cosmos terrifies because it denies an outside, leaving space as a closed hole floating in nothing. An infinite cosmos terrifies because it overwhelms identity, dissolving uniqueness into endless repetition. A multiverse terrifies because it dethrones our universe, reducing it to one among countless others. And yet, each fascinates for the same reason. Each opens horizons beyond comprehension. Each invites the human mind into scales that transcend life, planet, even galaxy. To imagine such structures is to confront both the fragility of human perspective and the grandeur of cosmic possibility. Science stands here at the edge of knowledge. The data show flatness, expansion, and acceleration. From these emerge possibilities that lead either to infinity, to unbounded closure, or to multiversal proliferation. None can yet be proven. All remain alive. Philosophically, the choice among them is less important than the realization they share. The universe is larger than imagination. Whether finite or infinite, singular or plural, the cosmos resists containment. Its size may never be fully known, not because science has failed, but because size itself may be a concept too narrow for reality. Thus, the question of cosmic size unfolds not into an answer, but into a horizon of possibilities. Einstein, Hawking, Goethe, Lindahl reached into these mysteries, offering visions that challenge not only science, but existence itself. Each theory is both map and mirror, revealing the cosmos while reflecting the limits of understanding. The universe may be finite but unbounded. It may be infinite. It may be one of many. Each path terrifies. Each path. And in that tension lies the true measure of the cosmos, not in numbers, but in the boundless reach of the human mind to imagine beyond them. The question of cosmic size is not only philosophical, it is also empirical, tested against instruments built by human hands, across deserts and mountaintops, beneath oceans, and in orbit above the earth. Humanity has constructed eyes sharper than its own, machines capable of piercing the night and reaching back toward the dawn. Each one is an attempt to measure the immeasurable, to press against the edges of the observable universe and glimpse the shape of what lies beyond. James Webb Space Telescope, launched in December 2021, the James Webb Space Telescope is humanity's most ambitious window into the past, orbiting at the quiet Lagrange point 2, a million miles from Earth. Webb unfolds a mirror more than 6 meters wide, gold-coated and shielded from the sun by a vast silver sail. Its instruments see not invisible light, but in infrared, sensitive to the faintest, reddest signals, stretched by billions of years of expansion. With Webb, astronomers can observe galaxies forming just a few 100 million years after the Big Bang. These infant galaxies test our models of structure, revealing how quickly matter assembled and how far the cosmic web extends. Every faint smudge captured in its detectors becomes not just a picture, but a data point in the measurement of scale. By charting how galaxies cluster, by tracing how their light bends through intervening matter, Webb refines the very geometry of the universe. But Webb is not alone. It is one among a fleet of instruments, each designed not only to see, but to measure. Euclid and the cosmic cartographers. In July 2023, the European Space Agency launched Euclid, a mission dedicated to mapping the dark cosmos, where Webb peers into the deep past. Euclid surveys the wide present, scanning billions of galaxies across more than a third of the sky. Its task: to chart the large-scale structure of the universe with exquisite precision. By mapping the distribution of galaxies and the subtle distortions caused by dark matter, Euclid seeks to measure the influence of dark energy on cosmic expansion. The patterns it traces, acoustic oscillations frozen from the early universe, serve. They allow astronomers to measure how quickly the horizon retreats, how fast the universe grows, and whether its expansion aligns with theories of flatness or curves into alternatives unseen. Euclid continues the legacy of the Sloan Digital Sky Survey, which, from the year 2000 onward, has created three-dimensional maps of millions of galaxies. These surveys reveal the cosmic web itself, filaments stretching across hundreds of millions of light-years, knots where clusters of galaxies gather, voids where matter is almost absent. This structure, imprinted from the earliest ripples of the cosmic microwave background, has become a ruler against which the size of the universe is tested. The Vera Rubin Observatorium, a mountaintop in Chile. Another eye prepares to open. The Vera C. Rubin Observatory, with its vast 8.4-meter mirror and a camera the size of a car, is designed to scan the entire visible sky every few nights. Scheduled to begin its legacy survey of space and time in the mid-2020s, Rubin will capture tens of billions of objects, creating a dynamic map of the heavens unlike any before. By watching galaxies flicker and shift, by tracing supernova across cosmic distances, Rubin will refine measurements of dark energy's influence. It will detect new gravitational lenses, cosmic magnifying glasses, created by massive galaxies and clusters that bend light and reveal the distribution of invisible matter. Each observation will be another thread woven into the map of cosmic size, particle physics, and the invisible engines. Yet the question of size is not answered only by telescopes. Beneath the Earth, in a ring 17 miles long beneath the French-Swiss border, the Large Hadron Collider smashes protons together. At near light speed, its detectors capture showers of particles, fleeting signatures of the quantum fields that underpin reality. Here, physicists probe the vacuum itself, searching for hints of how inflation began, whether hidden symmetries exist, and whether the vacuum we inhabit is stable or temporary. The Higgs boson, discovered in 2012, revealed a new layer of the quantum fabric, but also deepened the puzzle. The Higgs field's properties suggest the possibility of false vacuums, states that could collapse into lower energy realities, spawning universes in the process. In such ideas, the size of our universe is not a single number, but one instance within a broader landscape of possibilities. Particle physics thus complements cosmology, where telescopes measure the universe's shape, colliders probe the mechanisms that may have set it in motion. Together, they chase the link between the smallest scales of quantum fields and the largest scales of cosmic expansion. Gravitational waves, a new ruler of Spacian, 2015. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in spacetime from merging black holes. These gravitational waves, predicted by Einstein a century earlier, opened a new sense beyond light. Gravitational waves travel unimpeded through matter, carrying with them information about distances and scales. When a binary neutron star merger was observed in both light and gravitational waves in 2017, scientists gained a new method of measuring cosmic expansion, standard siren, to complement standard candles. Each event provides not just a glimpse of cataclysm, but a yardstick for the universe itself. Future detectors, such as the space-based LISA mission planned for the 2030s, will capture lower frequency waves, tracing supermassive black hole mergers across billions of light years. These signals will stretch across cosmic history, refining the measure of expansion and testing whether dark energy remains constant or shifts with time. The missions ahead the coming decades are rich with ambition. The Roman Space Telescope, named after Nancy Grace Roman, the mother of Hubble, is scheduled to launch later this decade, with a field of view 100 times larger than Hubble's. Roman will survey the cosmos for signs of dark energy, gravitational lenses, and exoplanets, uniting scales from the galactic to the universal. China, Japan, India, and other nations prepare their own space observatories, adding to the collective reach of humanity's eyes. Ground-based instruments, such as the extremely large telescope under construction in Chile, will host a mirror 39 meters wide, capable of resolving the faintest galaxies near the cosmic dawn. Each mission sharpens the measure of scale. Each test refines the estimate of size. Yet none can escape the horizon that acceleration imposes. However precise the map, however deep the survey, the ultimate borders remain unreachable, receding faster than pursuit. The unfinished map together. These instruments compose humanity's greatest cartography, not of continents, but of the cosmos. Webb paints the deep past. Euclid and Rubin map the present structure. LIGO and future detectors listen to spacetime itself. The Large Hadron Collider and its successors probe the quantum fabric that may generate universes. Each is a compass pointing toward an unknown shore, and yet the map remains unfinished. The observable universe stands as a bubble of knowledge, precise in detail but incomplete in scope. Beyond its edge lies silence, regions that no mission can reach horizons that no data can breach. The paradox deepens. The more powerful the tools, the more clearly the boundary appears. The cosmos invites pursuit, but also enforces limit. Its size can be refined, estimated, constrained, but never fully declared. Reflection: these machines, these observatories, are not just instruments of science. They are extensions of human curiosity, embodiments of a species determined to ask questions larger than itself. From gold-coated mirrors in space to underground rings of colliding protons, from seismic arms measuring the tremble of space-time to cameras mapping billions of galaxies, each tool is a fragment of a greater pursuit. Together, they whisper the same truth: the universe is larger than we can ever hold. Its size is a moving horizon, receding with time, expanding with discovery, deepening with mystery. The tools refine the question, but the answer remains beyond. For perhaps the size of the universe is not a number to be known, but a mystery to be lived, a reminder that humanity's reach is both vast and small, stretched between quantum fields and cosmic horizons, forever measuring, forever wondering, forever incomplete. Every map, however vast, has an edge. For oceans, it is the shore. For continents, it is the coastline. For the Earth itself, it is the curve of the horizon. But in cosmology, the horizon is not a line one can cross. It is a wall written into the fabric of space-time, a boundary not of geography, but of physics. This is the cosmic horizon, the ultimate limit of vision. It marks the farthest distance from which light has had time to reach us since the beginning of the universe. Beyond it lies reality, still unfolding, but forever concealed. The photons that began their journey there have not yet arrived, and some never will, carried away by the accelerating expansion of space. The horizon is thus not temporary. T is permanenta, prison of perspective that no technology can ever breach. The cosmic horizon. Prisonim. Imagine standing in the center of a vast, glowing bubble. The edge of the bubble is not a wall, but a limit, the farthest signals that can ever reach you. As time passes, the bubble grows, light from more distant galaxies arriving at last. But at the same time, the expansion of space carries many regions away faster than light itself, locking their signals beyond reach. This is the paradox of the accelerating universe. The horizon expands, but what lies beyond retreats faster still. Some galaxies, visible today, will one day vanish from sight, their light stretched into invisibility. The prison walls are not static, but tightening. Each year, fewer galaxies remain within our observable sphere, as if the cosmos itself is closing its gates. No telescope, no matter how vast, can reverse this. Light speed is absolute, an ultimate limit woven into the equations of relativity. Even a perfect instrument, detecting every photon with flawless precision, could not outpace the horizon. The limitation is not technological, but physical. Not in our tools, but in the structure of reality itself. Why physics forbids knowing all? Einstein's relativity binds measurement to the speed of light. Nothing can move faster, not signals, not information, not thought. Space-time itself, however, may expand, at any rate. And when space expands faster than light, regions recede into permanent exile. This is not a loophole, but a law. It ensures that all can never be known. The observable universe is not the universe itself. It is a bubble of knowledge defined by time and light. Beyond it, galaxies may exist, structures may form, perhaps even laws may differ, but their signals will never reach us. The cosmos is divided into two domains, the seen and the unseen, the measurable and the unreachable. Some physicists describe this as the cosmic horizon prison. Humanity is confined within a sphere, not by walls of matter, but by the geometry of space-time. The prison cannot be escaped, because it is not a cage within something larger. It is the totality of what can ever interact with us. Outside lies the unknowable, a realm real but inaccessible. The futility of perfect instruments throughout history. Human ambition has built ever finer instruments, telescopes that reveal the faintest galaxies, detectors that sense gravitational waves from distant black holes, colliders that smash particles to uncover hidden fields. Each step reduces uncertainty, sharpens measurement, and pushes boundaries outward. Yet here, at the edge of the cosmos, progress confronts futility. No lens, however large, no mirror, however polished, no detector, however sensitive, can surpass the horizon. The photons have not arrived. The signals do not exist within reach. Even if one could harness all the energy of a galaxy to build a perfect telescope, the prison walls would remain. The expansion of space itself is the barrier. It stretches distances faster than any probe can travel, faster than any signal can return. Even a spacecraft moving at near light speed, launched toward the edge, would never catch galaxies carried away by space-time's relentless drift. The universe enforces its secrecy, written not in stone but in mathematics, the emotional weight of limits for a species defined by exploration. The realization is profound. Human history has been a story of frontiers crossed, mountains scaled, oceans crossed, skies mastered, planets reached. Each horizon, once distant, was eventually overcome. The stars themselves, though distant, feel like destinations that technology might someday approach. But the cosmic horizon is different. It is not a challenge of engineering, but of ontology. It is not far, it is forever. The emotional weight of this truth cannot be ignored. To confront a boundary that cannot be crossed is to confront the limits of human knowledge itself. The universe, vast and magnificent, holds secrets that will remain secrets, not for centuries or millennia, but for eternity. And yet, within this weight lies something unexpectedly beautiful. For the cosmic horizon is not only a prison, it is also a reminder of privilege. Within our observable bubble, we witness galaxies, stars, and cosmic history on a scale that future observers may not. Billions of years from now, accelerating expansion will carry most galaxies beyond sight, leaving only local clusters in the night sky. The evidence of cosmic grandeur will vanish, erased by the retreating horizon. Humanity and life in this moment of cosmic time stands in an era uniquely rich with knowledge. The philosophical acceptance of limits. What does it mean to live within a universe whose totality cannot be known? Philosophy has long wrestled with the idea of limits, from the ancient Greeks who wondered about infinity to modern thinkers who speak of the unknowable. The confrontation with boundaries is as old as thought itself. In science, limits are often temporary frontiers, awaiting discovery. But the cosmic horizon suggests something different, a limit eternal, written not in ignorance, but in the very laws of existence. To accept this is to accept that knowledge has an edge, and that beyond it lies mystery that will never be resolved. Yet this acceptance is not defeat. It is humility. It is recognition that the universe is not designed to be conquered by thought, but encountered with awe. That human knowledge, though vast, is a subset of reality, and that mystery is not the absence of truth, but part of its essence. Perhaps, then, the horizon is not a wall, but a mirror. It reflects back the limits of perception, reminding that curiosity itself is infinite, even when knowledge is bounded. The prison is also the cathedral, a space where limits sanctify wonder. The limits of measurement define the cosmos as much as expansion, dark energy, or infinity. They remind that the universe is larger than ambition, deeper than equations, and more mysterious than discovery alone can hold. And so, the final paradox stands clear. The more humanity measures, the clearer the horizon becomes. The clearer the horizon, the stronger its permanence. The size of the universe is thus both known and unknowable, measured within the bubble of light, but forever incomplete beyond it. To live with this is to live with mystery. To accept the prison is to embrace wonder. For within the limits of measurement lies the greatest revelation of all, that the universe is not simply to be known, but to be marveled at. The search for the universe's size leads, finally, not to numbers, but to reflection. Measurements stretch across billions of light years. Theories reach toward infinity, and yet the question remains unresolved. Perhaps it was never meant to be resolved. Perhaps the very act of asking reveals more about humanity than the cosmos itself. What it means to face infinity. If the universe is infinite, then it is not simply large. It is without boundary, without totality, without end. Infinity denies summation. It resists completion. To confront infinity is to stand before a mirror of thought itself, always extending, always receding, always unfinished. For physics, infinity is both a tool and a terror. It simplifies equations but breaks predictions. For philosophy, it is a horizon of imagination, stretching the mind beyond its own capacity. And for humanity, it is an emotional paradox. Infinity makes the individual feel smaller than a grain of dust, yet also part of a scale so vast that smallness loses meaning. In infinity, nothing is central, but nothing is excluded. Every atom belongs. Every life participates in the whole. Human smallness and human significance. The night sky humbles. To stand beneath it is to feel the weight of distance, the silence of space, the fleetingness of life. The earth is a world, yet compared to the universe, it is a mote suspended in a sunbeam. This image, first voiced by Carl Sagan in his meditation on the pale blue dot, captures the fragility of human existence against the cosmic backdrop. All of history, all of civilization, every joy and sorrow, every triumph and cruelty has played out on a speck adrift in vast darkness. And yet, within that smallness lies significance. For it is precisely from this fragile world that questions of infinity arise. From this pale dot come beings who measure, calculate, theorize, and dream. Smallness is not erasure, it is context. Against the infinite, the finite gains poignancy. The very brevity of life makes wonder possible. We measure, not because we expect to grasp infinity, but because longing itself is human. To look outward is to express something essential, to seek meaning beyond survival, to stand in awe at scales that dwarf comprehension. The pursuit of cosmic size is not only scientific, it is existential. Einstein's cosmic religious feeling. Albert Einstein spoke of what he called the cosmic religious feeling, a sense of reverence, not for doctrine, but for the vast order of the universe itself. For him, to contemplate the laws of nature, to glimpse the harmony of mathematics with reality, was to experience awe in its purest form. The size of the universe evokes this same feeling. It is not comfort, but humility. It is the recognition that the human mind is both small and extraordinary, that it can ask questions whose answers stretch beyond its reach. Einstein wrote that the most beautiful thing we can experience is the mysterious universe's immensity ensures that the mysterious will never vanish, the horizon will always retreat, the scale will always surpass, the mystery will always remain. Sagan's pale blue dot revisited. Carl Sagan, gazing upon the image of Earth captured by Voyager 1 in 1990 from 6 billion kilometers away, described our planet as a pale blue dot. In that reflection, he found humility and responsibility. The dot was home to everyone who ever lived. It was small but precious. Viewed through the lens of infinite scale, the pale blue dot becomes even more poignant. Against trillions of galaxies, against the possibility of boundless universes, Earth's fragility deepens. Yet so too does its significance. For within the silence of infinity, the dot is not anonymous. It is known, loved, and seen by those who inhabit it. It is where consciousness gazes back upon the cosmos, where infinity becomes personal. Sagan's reflection becomes not a diminishment, but an elevation. The dot is not important because it is central, but because it is capable of wonder. Against infinite vastness, wonder is rare. Against infinite repetition, meaning is fragile. The dot's significance is that it asks the question at all. The horizon as mirror, the cosmic horizon, unreachable and permanent, is also a mirror. It reflects not only the structure of space-time, but the structure of thought. Every observer, anywhere in the cosmos, stands at the center of their own horizon, bounded by the reach of light. This universality is humbling. No place is privileged, no perspective complete, and yet it is also empowering. For within each horizon lies the same truth. The cosmos is larger than the mind can hold, but the mind still reaches outward. The act of reaching is itself the answer. The size of the universe may never be measured, but the measure of humanity is found in the attempt. Living with mystery, too. Accept that the universe's size may be unknowable is not to admit defeat. It is to embrace mystery as part of existence. The horizon is not an error to be corrected, but a reminder that limits define beauty. Just as music arises from silence between notes, so too does wonder arise from boundaries we cannot cross. Mystery endures because it must. Were the universe fully knowable, awe would diminish. In the unmeasurable, awe finds permanence. The cosmos ensures that curiosity never exhausts itself, that imagination never ends, that wonder always has room to grow. The the true size of the human spirit, the question of cosmic size, leads finally inward. The universe may be infinite, but so, too, is human longing. The mind that gazes outward is itself a universe of thought, capable of imagining what it cannot hold. Perhaps, then, the size of the universe cannot be declared in numbers, but in the capacity it awakens within us. Its immensity expands not only horizons, but hearts. Its mystery enlarges not only knowledge, but spirit. The universe is immeasurable. But in asking the question, in daring to measure, to imagine, to wonder, humanity reveals its own true scale. Closing. Reflection beneath the silence of stars, beneath the infinite night. One truth resounds. The universe is larger than knowledge, deeper than science, more mysterious than imagination. Its size cannot be captured. Its horizon cannot be crossed. And yet, in standing small beneath it, humanity becomes vast. For the size of the universe may never be known. But in asking how big it is, we reveal the measure of ourselves. The cosmos is infinite. So too, perhaps, is the human spirit.